Okay, so in the previous two videos, we've tackled the problem of a particle in a box. And we've done it in two distinct ways, either having the potential going from 0 to L, being 0 and infinite elsewhere, or being symmetric relative to the origin. But these were two special cases. What I would like to do now is solve the problem for a general potential that is defined as follows. It is infinite everywhere except for a region for an interval from A to B where I define L to be B minus A. So that's the length of our box, of our one-dimensional box. And the potential can be formally written as follows. So it can be inferred as to be 0 in the interval from A to B and infinite elsewhere. Now again, what we would like to do in this case is solve the Schrodinger equation to get the energy eigenstates with the corresponding eigenvalues for this generalized case. Obviously, we have three regions of interest, region 1, region 2, and region 3 as follows. So now regions 1 and 3, we will have, as usual, psi will equal to 0 because the particle will have finite energy. And no particle with finite energy can exist in a region of infinite potential. So psi will equal to 0. So that leaves us with region 2, where the potential is equal to 0. Then the differential equation becomes minus h bar squared divided by 2m. The second derivative with respect to x of psi is equal to e psi. And multiplying by the constants and rearranging the equation, we have d psi squared of dx squared of psi is equal to minus 2m e h bar squared psi. And so we can get this to be k. We define this to be k squared. And so the equation becomes d squared psi by dx squared is equal to minus k squared psi. And this is a well-known equation, as we said before, and we get the solution is, and this time I would like to write it as a sum of complex exponentials. So it's a exponential ikx plus b exponential minus ikx. And we can check if this wave function that I've written is actually a solution to this equation by calculating its second derivative. So the first derivative of psi will give us the a and b are constants, so the derivative of a complex exponential, you just drop whatever is next to the x, so it's just ik, a exponential ik x, plus, well, here also what's in front of the exponential will be minus ik, so you drop it here, b exponential minus ikx. And we do the same thing again to get the second derivative of psi with respect to x, and we get, you drop the second ik to here, and so you get ik squared, a exponential ikx, plus, again, you drop the minus ik again, so you get minus ik squared, b exponential minus ikx. Now, this part is squared, so the negative sign is kind of redundant. We can swap it for a positive, and we can take this whole expression to be common, so we'll get that d squared psi by dx squared is equal to ik squared into a exponential ikx plus b exponential minus ikx. We note on the side that I squared is equal to minus 1. So we get that, and if we observe this equation, this is just psi that we defined earlier. So we get psi here, and rewriting it finally we get that d squared psi with respect to x is equal to minus k squared psi, which is indeed the equation we had earlier. So psi is indeed a solution to that differential equation. So psi is a solution, but we still have the boundary conditions to worry about. And what do the boundary conditions state? Well, we just said that in regions 1 and 3, the wave function must equal 0 because the particle must have finite energy. So psi at the point A must be equal to 0 because it must be a continuous function. And psi must also vanish at point B because it must be also continuous on that side. So we'll have two boundary conditions which state that psi at A must equal to 0 and psi at B must equal to 0. We get the following two equations. So A exponential IKA plus B exponential minus IKA is equal to 0. And you have A exponential IKB plus B exponential minus IKB is equal to 0. So you have these two equations that we got, and we need to solve for A, B, and K. Now, if we observe the first equation, we can rewrite one as follows. So B exponential minus IKA is equal to A exponential IKA with a negative sign here, and multiply the entire thing by exponential IKA. And our goal is to get rid of this complex exponential to the side of B, and we have B equals minus A exponential 2 IKA. And so that's our first result. So we got B in terms of A. But we can rearrange this further to have the fraction B over A equals minus exponential I 2 IKA. Similar arguments can be followed with equation 2 to get the fact that B over A must equal minus exponential 2 IKB. But notice that B over A must equal B over A. So this one must equal this one. So what we get is B over A equals B over A. And we can say that minus exponential 2 IKA must equal minus exponential 2 IKB. The minus signs are redundant, so we can multiply by an overall negative and divide or multiply both equations by minus 2 IKA. And what we get is that 1 must equal exponential 2 IKB minus A, which is otherwise known as L. And you have yourself 1 must equal I 2 K times L. Now, this is a complex exponential. So if we observe the complex plane and write a complex, so this is the real axis, this is the imaginary axis, and this is some complex number. It has some angle and some which is some phase and some magnitude r. And remember that any complex number can be written in this form r I theta. In our case, the magnitude is 1 and the theta is 2k dot L. Exponential I 2k dot L equals 1. That means the theta must equal to 0, or theta must be some integer multiple of 2 pi, which implies that 2k L must equal 2n pi, which implies that k is equal to n pi over L. That is, we've determined our k values, which appear to be quantized, and from k we can infer that E is equal to h bar squared k squared over 2m, which also in turn implies that E sub n equals h bar squared divided by 2m n pi over L, all of it squared. So we've determined our energies and they appear to be quantized and are in multiples of the integer n. Now we go back to our wave function psi of x, which equals a exponential I k of x, plus, instead of b, I would like to substitute for b this expression that we found earlier, which is minus a exponential to ika. So here we have minus a exponential to ika exponential minus ikx. And we can take a and a exponential ika as a common factor from both equations. That leaves the first term doesn't have an exponential ika, so it'll gain a negative exponential ika in order to counteract this constant that we pulled out. And you have exponential ikx, it's already there, minus exponential ika exponential minus ikx. You get that psi of x will equal a exponential ika, v written in this form, ikx minus a minus exponential ik minus ikx minus a. And now this is very close to a sine. So if you remember that sine of theta equals exponential I theta minus exponential minus I theta divided by 2i. This closely resembles this, right? But not quite. We still are missing the 2i, which is simple. It's just a constant. So we just multiply, divide by 2i, and multiply by 2i. And this whole expression just becomes a sine. So our psi of x will become a 2i exponential ika sine of k, but this time we'll substitute the value of k, n pi over L x minus a. And you get, this is your wave function, which is a little bit odd. You have an additional complex factor and an additional 2i here. But remember that psi and c times psi, where c is a complex number, have the same physics. Meaning that physics and the probabilities all depend on psi squared. The complex number will just add a scaling factor and some complex phase, which is really irrelevant to us physically. So we can drop the 2i and exponential ika because they're complex constants. A, on the other hand, is a normalization constant that we've derived in the previous videos, and we know that it is equal to square root 2 over L, which is the length of the box. So you get that psi sub n of x is equal to the square root of 2L sine of n pi over L into x minus a, and with the corresponding energy eigenvalue of h bar squared divided by 2m n pi over L, all of it squared. So this is our generalized solution for a potential well that is bounded between an interval a, b, a generalized interval a, b. Doesn't have to be symmetric or near the origin. This is our generalized solution. And we can immediately see that if a is equal to 0, we get our asymmetric solution. But what about the case where a is equal to minus L over 2, the symmetric well? Well, let's just dive deeper into that solution to understand where the cosine and the sine and the odd and even numbers come from. So in that case, we'll have that sine, the psi n of x will equal to the square root of 2 over L sine of n pi over L x minus a, and a in this case is minus L over 2, so it's going to be plus L over 2. And I would like to just observe the sign, how it will behave depending on, if we expand within this bracket, we'll get that it's n pi over L x plus n pi over 2. Now adding pi n multiplied by pi over 2 will do things to the sign depending on if n is even and whether it's odd. So we'll have different kinds of behavior for the function if it's even or odd. This is not physical. This is just pure trigonometry, because remember that if you add from the unit circle, if you have, this is theta, this is your cosine of theta, and this is your sine of theta. Okay, so let's take the case where n is even, which means that n equals some integer number m multiplied by 2. We can substitute that and get that psi of 2m of x will equal to the square root of 2 over L, the sine of 2m pi over L x plus m pi, because the twos cancel, so you're adding a pi to your sine, adding a multiple of pi, so you can either add 1 pi and you end up here on the unit circle, and this is just gonna multiply the sine function. This you'll get the exact same sine function but multiplied by a negative. So remember that sine of theta plus pi will equal to minus sine of theta, while sine of theta plus 2 pi will equal the sine of theta. And any multiple of these two, so if you had 3 pi here and 4 pi there, it's always going to be, it's either going to be a minus sign or a positive sign. And since the physics does not change if you multiply sine by some scalar value, then the plus m pi is redundant and we can drop it, so you get psi m of x is equal to square root 2 over L sine of 2m pi over Lx with the corresponding energy eigenvalues E2m equals h bar squared over 2m pi over L squared. So would you look at that? We got the exact same solution for the even functions that we got earlier from that wave function, from the solution that we got for the symmetric well. Well, what about for the case where n is odd? So n is odd, so n will be written as follows. So n equals 2m plus 1. We'll get that psi of 2m plus 1 of x will equal to square root of 2l sine 2m plus 1 pi over L plus 2m plus 1 pi over 2. Okay. And so expanding this into that, we get the square root of 2 over L sine. So again, we have the situation where we have a multiple of pi, but we said earlier that that value is redundant. It only changes the sign of the sine function, but we don't care about the sign because the physics remains the same. So this, we can drop that term, but we still here in this case, in the odd case, we still have a pi over 2. And so the sine of theta plus pi over 2 will change the sign from a sine to a cosine function with some term, it's either positive or negative, but we don't care in that case. So we can write the odd functions psi 2m plus 1 sub x will equal to 2 the square root 2 over L cosine 2m plus 1 pi over L x. There's an x here and an x there. So that's our solution for the eigenstates, and you get the energies 2m plus 1 And so we get the exact same solution that we got from the symmetric well, but with the odd and even functions back. And the reason that we had odd and even functions to begin with is that sine and cosine functions act differently when phase shifted by a pi over 2 or a multiple of pi. Hence, the difference of wave functions, which is entirely dependent on the properties of the trigonometric sine and cosine functions, and is completely independent of the physics of the problem.